All right. We're live. Let's make sure we got everything out. We got. Can you hear me now? Can you hear me now? I think you can.
That's your phone. Chicken.
I don't know.
I didn't.
Hey there, y'all. Still working on the glitches here. YouTube doesn't seem to show me as sending anything, but I guess I am.
Because you're live.
Because apparently I'm live. Oop, I don't understand. Aha, there we go. Now I've got it. Hopefully you can hear me. Let's see, we'll pop this out.
Yes.
And then we can go where I'd rather be going here. All right.
But you can't see the chat.
I can't see the chat.
I can't see the chat. In the
On the phone or?
no, I took it off the phone. I'm on the computer. Oh, there it is. I got it.
All right.
And he said now you can hear.
And now we're working it all
Yay.
out. Yay! Good to finally talk to you here. Live. So, we have last left off and last left off again. And where we're at now is we have Hello World and a repetitive rather. Hello Worlds from YouTube over and over again. Then it just hits a stop and we run it. So let's take a look at that program. So at the very top we say where we want our program to start, and then we start our program at that location. And everything that isn't this bluish color is not actually being read or executed. So everything in between, everything else is a comment of some sort. So I may not write my programs quite so well commented in the future. So you can kind of see this line would be the C or C++ line. The next line is the actual assembly as it would be written if you were going to write it in assembly and read it. And then below that is the actual machine instruction. So this is kind of like mixed mode programming. So those instructions through here write each individual character out by themselves, and then we halt. So if we show that by reset, you can see that hello world prints really fast. And that's because it's just going one byte after the other. Print the H, print the E, print the L, print the L. Now when we say go and it starts printing that whole string, it's a good bit slower because it's actually running in the loop saying print the H. Actually it's saying load the H. Is the H a 0? No, print the H. Load the next character. Actually, we'll get it all to be exact. And we'll show you the actual code here. It is load a character. First off, here we go. First off, say what we want to print, which is at this location. So we load that into the data pointer register. Then we say load a byte from wherever this data pointer register is located. And then if it's a 0, we're going to jump past the next few bytes. And if it is not a 0, we'll fall through. In this case, we just write that byte out to the output port. Then we're going to increment the data register to the next byte and jump back up to 43, which is load a byte. So that's just going through the loop, looking at each byte and printing it over and over again. I should really get off this. We don't need all this extra stuff. Here we go, where you can see the whole system. So we went from straight line print to now if we say hello world, and we can just change this S here to a 0, 0. Save the file. And then inside the computer, inside the processor, is the ROM. And we will reload our ROM image.
Is ASM the name of the language?
Yes, it's assembly. Generic assembly. I should say assembly is the language, the name of a language. How to describe that? Assembly is the sort of lowest level language writing other than writing the bytes directly. Like in our previous video, we just put the bytes into the ROM directly, one after the other. And now the next level up from that would be writing in assembly, which is generally a 3-letter mnemonic for each instruction of the processor. So the instructions of the processor are things like load a byte from a particular location, print a byte to a given port, and this grid here shows you the connection between the mnemonic. So LDR is there. So LDR is actually the 7-6 instruction in machine language. And that instruction says load the data register with the next 2 bytes. And so on. So we'll actually single step through this in the next bit.
He says that's very interesting. It's thinky man.
All right. Let's get this back in view. So if we reset, you see how quickly that prints? We'll do it again. Foop, foop. Now we tell it to print hello world character by character. Actually does it twice. Why are you doing it twice? Why did you do that twice? So there's loads up that. So yeah, we might want to say, man, let's go debug why it's doing it twice. That would be a bit of a problem. So, oh, well, this will be why. Hate when I find it by inspection before I actually look through things. Yeah. Here comes the puppy. Must have a puppy break. I know, it's very early on. But here's the puppy. Murr. What do you murr? Murminer. She's got
What are you doing?
I wanna do something. Quit looking at the blinky box. Alright, you good?
Hi.
Say hi. Murminer. Murminer. Alright, close enough. Always, every time I sit down to do something like this, in comes a puppy. So, I think I know the problem. This instruction is 97, which is not a halt instruction. So right here, when we said jump a small distance, if it is not 0, and what it means by not 0 is when we load into the B register, LBF, load into the B register from flash or ROM, but so part of the benefit of building your own processor is you can create your own mnemonics, your own language. So for my assembly, every instruction is 3 letters. Other instructions or other assembly languages may just have a J or a JS or a JL instead of a JSN and a JLN and that kind of thing. So it's kind of arbitrary. It's one of those things you got to go look up the instruction set for each individual processor that you are writing this low level at. But we get to make it up as we go along. So anytime we load into the B register a value from anywhere, it will set the 0 flag, or not 0 flag to be exact, depending on whether it's 0 or not. So right after we load that B, we can then check the flags, the 0 or the non-zero flag, and this instruction, jump a small distance if it is non-zero, and the location to jump to is indicated by this vertical bar symbolism. Again, none of this is actually compiled or assembled, so I'm kind of just making it up as a way to indicate that this says jump to 47, and 47 happens to be where the PI is. So this is, eventually I'd like to get to where I have an assembler and all of these light blue lines go away, and I can just say, write directly in assembly JSN some location name and then give that same location name here, and the assembler will figure out what all these numbers should actually be. That'd be the main value of an assembler. So we actually don't want that to be a 97. We want that to be an 11, which is a halt. So halt instruction 1 1. And of course, obviously, once you start playing with this for a little while, you just start remembering them. So save that off, jump back over, and go straight in. I wish I could do this externally, but load the image. Go back to desktop view, reset, go, reset, go. That doesn't look right either. Yeah, well, this is what live coding is. At least it stopped doing it twice. Now, why does it seem like I'm getting sort of a reset? Right? Well, let's single step. This is what you end up doing a lot when you're debugging. So let's see, we got, here's the computer level. This is, which would be roughly the equivalent of the internal of the computer case. So there's your external view. It's just a monitor. You can reset and run and that kind of thing. But as if we rip the case off the computer, this is the internal guts. You got your processor here. It's actually a microcontroller, which means it has RAM and ROM all built in. And double check, make sure I'm talking. And you could sort of debug and single step from here as well, but that doesn't give you the full information or the full view of what's going on, because each instruction takes more than one clock cycle. So when we single step in Logisim, every time we take a step, it's one clock signal. Some instructions take 1, 2, 3 multiple clock instructions. And so you don't necessarily see everything change at this view. To see everything about what's going on inside the processor, we have this view. And in this view, you see we have the A register, B register, temporary register, what we refer to as the data register or data pointer. And those are the things that you actually operate on and do things with. And then the registers over here are the internal functional registers. So the instruction register is the instruction you're running right at that moment. The instruction pointer is where in the ROM is the current instruction, where you want it to create the next instruction. And then the stack pointer, which we have yet to get into because we're still writing codes step by step. But suffice it to say, what the stack pointer allows is to store where you're at so that you can jump someplace else, do whatever it wants to do someplace else, and then jump back to where you left off.
He said he loves how you can use simple things like logic gates to create complex things.
Oh yeah, there's a lot of logic gates in this. But part of this, sort of the model of this was based off of the 8051 microcontroller from Intel. And the driving factor in the 8051 microcontroller was we can only build a processor with so many transistors. So instead of the multi-million or trillion transistor chips that we have now, this would have several 100,000 perhaps. And or several thousand, not even 100,000 transistors. And one of the ways they got away with doing that was the ALU, which does all the math. So if you put a value in the A register and put a value in the B register, and then you say you want to add those together and put the result back in the A register when you're done, to do that in parallel, you would need an ALU, an arithmetic logic unit, that could sum 8 bits at a time. Doesn't sound terribly difficult these days, of course, and the number of bits that you can do calculations on at the same time, or is where you would get your bus width. Or in the case of Nintendo, your Nintendo 64 could do calculations on 64-bit numbers in parallel. And your 16-bit machines would be your 286s back in the late 90s. Your 32-bit machines in the early 2000s. Your 486 machines were 32-bit, and then you had your Nintendo 64, and now a lot of these processors have even 128. But that's all because they have lots and lots of transistors. They can do calculations in parallel. When you have very little number of transistors, you do all your calculations one bit at a time in serial. So we'll actually do one of those here in a bit. But first we want to find out why it seems like we are clearing the screen. Let's see. 20. Forty-seven increments, jumps back. It looks correct here. Is there a 96 there? Where's that 96 coming from? There should not be a 96 at address 00221, I guess it would be. Oh, that's because we're looking at 46, and that's 21. So let's keep scrolling down here. Here we got 46, that's our 11. And that's because we're it is, come on now, we're at the end of the hello world. So let's stop the auto increment, reset, come back in. Here's our main processor. Now, as we start to boot from just raw power up, I'm going to hit the F9 button repetitively for the single step. And what's first going to happen is it's going to go through and clear these values and set them to their default. All of the registers to 0 and the stack pointer to FFFF. The reason the stack pointer starts at quadruple F and the instruction pointer starts at 0 is the instruction pointer in all of your code would grow upwards from 0, and the stack pointer grows down from the top of memory. And never should the twain ever meet, because then bad things happen. So let's see. So let's just start. We're going to do the first few of these pretty quickly, as it's just that blanking of values, and you can't really even see that.
Somebody says Y-O-T. Oh, V-O-T, FYI.
V-O-T.
V-O-T.
I'm going to have to spell that one out, I think. All right, so what we just saw was the 8 here in ROM was loaded into the temporary register. Our instruction pointer went from 0 to 1. Now we're going to read that 0. And you can't really see this either because we're reading that 0 into this location, which is already 0. Now we're going to take the 8 from T and put it over here. Now that's changed our instruction pointer. So this first 2 bytes in ROM is what we would call the boot vector. It's when I start from 0, the system starts at 0, and so generally you want to jump over a few other bytes. Some of these other bytes are for other functions like the interrupts, which we'll get into later. So we want to at least jump over those and get to 8. In a lot of systems like PowerPC systems, for some reason it starts at 40. Go figure. Or not even 40, 4000. 4000.
Alright, so somebody came in the room and put VARK.TECH in big words. I'm zero sure what that is.
VARK-tech. Sorry, Ruth Boot.
I don't know who those people are that are coming in and putting big stuff up, but then they're not saying anything else.
They're
not watching.
I'm going to have to Google Varktech, I guess.
They're not watching, so.
Let's googly the Varktech, why not?
VARK.te. Probably some stupid crap.
Varktech deep dive.
So they're just dumbasses going to see live streams and putting stuff in their thing and leaving?
Watch out for Varktech comment bots. Yeah.
Alright, well,
Let's see.
block them.
You got a wrench, right? You can toss those,
I'm gonna
right?
block them.
I don't know what VOT.FYI is either.
Unwanted commercial content.
I don't know if it's commercial, but
I don't know. I'm gonna put it as content or spam. So
whatever.
Spam them.
All right. We're not too active in the streaming side of YouTube, so I'm not sure what all the details are, but
all right. I just wanted to know, so thank you for letting me know. Now you know.
that'll work. And let's see. Where, pray tell, did we leave behind? We were single stepping. There we are. Yes, of course there's notifications. So, we'd managed to load up 8000, and this is because the smaller address, the lower end of the address, so this is the address, all 4 nibbles, 2 bytes. But the lower byte comes first, that's called Little Indian. It's the bane of my existence. One of the banes of my existence is the fact that some systems put the lower byte first and the higher byte second, and others, big Indian systems, PowerPC, and just about every software or every processor design since they didn't have a serial ALU. Oh, what fun. It's what time is it now?
6:10.
6:10, and it's dark out, and there's somebody with a leaf blower.
It's my next door neighbor.
There's always a leaf blower when you go live.
It's the next door neighbor.
I don't know if you can hear it, but I can.
I can hear it. I can see what you're doing, and I can see.
Alright, we're back from that. Sorry. So, this is a little Indian machine, and much like almost everything that's Intel, even today, even though they have enough transistors to do everything in parallel, and it shouldn't matter anymore, Intel is still little Indian. The entirety of the internet is big Indian, by the way. So on your Intel machines, every time 2-byte packages or 4-byte values come across, if a 32-byte value shows up on your network, your card has to flip the bytes around in order to go from big Indian to little Indian. So just for that reason alone, PowerPC machines, Macs, mostly Macs at this point, if they still are, would be slightly faster. So we've loaded up our address pointer. Now our new instruction, our next instruction, is going to be at location 0008. That instruction 0008 is a D1 instruction, which every other instruction is a D1 instruction. And if we look back at our reference, D1, which is here, is write 1 to E, or write to port 1 from EEPROM, if you decipher it all the way.
He said it's 11:10 there. It's only 6:12 here, and my neighbor is.
Yeah, but it's dark out, so I guess he does have a lot of lights. So D1 is the instruction. It says we want to read this next byte in ROM, or EEPROM, and stick it out to this one output port. So one of the big differences between a microcontroller and a microprocessor is that the microprocessor doesn't have built-in RAM and ROM. All of that is external to the processor, and the processor usually doesn't have multiple serial ports or multiple parallel ports. It may have one or two, but those then go to an expansion chip that then spreads it out and provides USB and all those other peripherals. So, but the point of a microcontroller is to have also the main processor clock is usually external on a processor. So if you went out and you bought a PC and you bought the main processor, the motherboard would be where the clock is, and also the RAM is on the motherboard, and everybody's familiar with buying computers with more or less RAM nowadays. ROM is the embedded equivalent of a hard drive. Not at all that they operate anywhere near the same, but it's your permanent storage that's still there from reboot to reboot, versus RAM, which is cleared every time you restart. So, long story short, we're going to sit here and say D1. We load that instruction into the register. Then we have D1 moves the instruction pointer over, reads that 48 and puts it down here. Now if we look at the desktop view, well, and we'll have to take it one more step. There we go. One more step to get that H all the way out of the system and onto the console. And so next instruction, D1, do the same thing again, but this time with a 65 hexadecimal, which is a lowercase e. Then do the same thing with the L, which is 6C, and L again, O. So by that time, we should have hello all printed out. All right, so we could continue single stepping while it prints the world part, but if we just let it auto run or auto step, it'll run through the rest of the world, print out world exclamation mark, and then stop at this halt instruction. You know, the halt instruction hasn't stopped the clock from going. What it's done is it's turned off the clock, and that's actually covered in our other video about the tick-tock of the master clock. So I'm going to stop the manual clocking, clear that clock flag, and now I can continue to do single step. So sure enough, the next step is a 96 instruction. 96 instruction is not really what I want to do. It's we're going to do it later, but right now we don't want to do it. But a 96 instruction is the call function. So that's call a subroutine is that instruction. What we really want to do is just jump a long distance to the next instruction that we want to print. So that would be the 90 instruction. Now we can test this by just changing it here, but obviously it would be better to come back and change it here, or to be more exact, change it here. Now the difference between a jump and a call is, as I briefly stated before, the jump stores where you're at so that when you come back from what you're doing, you can continue where you left off. So we're just going to say jump to that location, and it would continue from after that to doing whatever it's doing. So let's see. We're going to jump. We want to jump to 43. So it loads 43 into the temp register. Then it increments the instruction pointer, and it's going to read this 00 into this part of the instruction pointer, which of course you can't tell, right? And then we're going to move this 43 into the lower part of the instruction register. Now our next instruction is going to come from 0043, which is exactly what we told it to do, except this was 90. So that's going to jump down to 4.3. And if we do that, though, we've skipped this instruction. So right now, the data register is pointing to 0. If we run from here, we're going to start printing out all of these bytes that are not what we want. So we really don't want to go to instruction 4.3. We want to go to instruction 4.0. There's a number of ways of fixing this. We could do it all correctly and fix the code and reload the code all like that, which I guess maybe we should, and then we'd have to restart and so on. Or we can just back up the instruction pointer by 3. So let's look inside what the instruction pointer is. And this is your instruction pointer register, which is a bit confusing, but ultimately it is 16 1-bit flip-flops. 8 1-bit memory locations that can be either 1 or 0. Now, this is also Little Endian, meaning this bit over here represents the least significant bit, or the ones place. This is the 2's place. So if we get rid of the 2's place, oops, we changed it to 41 instead of 43. And you see we've moved in there as well. So let's go back in there, get rid of the 1, go back up. Now we're back at 4.0. Now, obviously with most computer processors, you don't get to go in and fiddle with the instruction pointer like that. Luckily it's virtual, so we can. So now we're going to do the instruction. The next instruction we're going to load is 7.6. And 7.6 says load the next 2 bytes, which are in this case are 50 and 00, into the data register. Now, luckily the data register doesn't have to do the same work, so I could build it out of some stock registers inside Logisim. So all of those individual flip-flops that you saw in the instruction register are actually down inside this box. So let's see, we want to make that, well, we want to make it something. We're going to overwrite it anyway, so we're just going to throw some random stuff in there. So now it's 2924, whatever, right? This instruction, when we start single stepping again, whoops, be like that. I didn't catch it at the right sub instruction when I changed the instruction pointer. Hate when that happens. Now we load 76 into the instruction register. That instruction says move the instruction pointer 1 over to take that 50, throw that in that part of the data register. Now move the instruction pointer over 1 more, read this 00, put that there in the data register, and that's the breakdown of that 76 instruction, or load into the data register the next 2 bytes, as it were. So now we're back at the 43, location 43. I should say 4.3. It's not 43. These are not decimal numbers. They're hexadecimal. So usually the convention is to just name the individual digits. So here we are at instruction 4.3. We're going to load into the B register from flash or EEPROM, as the case may be. And so we're going to load from the location pointed to by the instruction pointer. So if we start single stepping, we load the instruction. Now we've said instead of using the instruction pointer to look at the EEPROM, we've passed a sub instruction that says use the data register to look at the EEPROM. And so now the data register address of 50 is being used. And we're going to take that 48 that's located there and load it into the B register. That was load into B from flash, right? And the last thing we have to do in the sub instruction is throw the bus back to the instruction pointer. Otherwise, we're not going to be looking at the right place when we try and do the next instruction. You can see how all the ways these can go wrong. So now we have that, we loaded the 48. And now we're going to do 82. 82 or 82 is the jump short, meaning only the lower 2 bytes, or the lower byte of the instruction, or jump short. Jump just by the 256-bit offset of the lower byte. If the non-zero flag. So when I was talking about flags earlier, these are the flags I was talking about up here in the top corner of the ALU. And there is a borrow flag, a carry flag, and a zero flag, or non-zero really. So because we loaded a 48 into the B register, the ALU reset to say, is the 48 something other than 0? And if so, then light up the 0 flag. These flags are then pumped into the instruction sequencer so that when I do something like 82, it has those values available to make decisions with. Now we're going to take our 82, bring that in as the instruction. It's 82 increments to the next location. And if the flag is set to non-zero, it's going to take this next value, 47, and throw it into the low end of the instruction pointer, which it did. And what that did was skip over location, let's see, that is location 47, which is the halt instruction. Go back at our instruction, our code. Sure enough, we jumped past 46 to 47. Now we can continue from that. The next instruction is the D4. D4 is write that character that's in the write to port 1 from B. This is port 1. This is B. And port 1 still has the hex 21, which is the exclamation character. This instruction is going to take it and boom, their register, the contents of B were copied over here to the port. So now that we've done the copy to the port, our next instruction that we load, DE, is we want to add 1 to this register so that we're not printing the same character over and over again. Which is, the instruction is called increment the data register, INC or increment, so IND. So increment the data register, which is BE. There we are. We've got these all coded, color coded, so all the increment instructions are this light pink. All of the moving instructions are the blue. All of the jumping or function call instructions are this brick. Then MAB, MAT, MBA, all of these instructions in here are minus instructions. Over here, the EAT, EBT, these are sum instructions, kind of trying to use the E as in summation. Again, these are totally arbitrary. You could define them however you wanted. So that's just the pattern I picked. So let's get back to incrementing the data register. So what do you think we have to do to increment the data register? We have to start off by selecting one of the constants out of this little constant generator. And in this case, that constant generator is set to 1. We load that constant into the temporary register. We then say we need to sum 1 and the data register. So we tell the ALU we're going to start a summation operation from the T register and the DR register, and we're going to put the result back in the DR register. And now what you're going to see is all of these little lights down here are the individual bits. And they're going to slowly march one bit at a time through the ALU, with the output coming back into the end of the data register. So you'll actually see these values walk across, if you will. Same thing happens with the T register as it goes. Then so now we've done the summation of 1 plus the low byte, which was 50 previously, but is now 51. But since this is a 16-bit value, not an 8-bit value, we now have to add another 8 bits. In this case, we want to add a 0 to the existing value to just basically shift all of those bits over. So now we add 1 bit at a time until we have 0051. And that took 16, 17 clock cycles to add 1 to the data register. Now, the stack pointer, being such a special feature register that almost is always either incremented or decremented rather than added to, it actually can't be added to. We can only increment or decrement. We can only increment or decrement 1 at a time. And that's the typical usage of a stack pointer, is to go up and down a small amount. What we really want later on is we're going to want to take the stack pointer value and bring that into the data register and then add some offset. And that's what's going to be able to allow us to get to parameters when we're calling a function and we have a lot bigger set of parameters. Right now, all of our functions, we can preset the data register to what we care to print and tell it to print, and then jump in there and tell it to print. Later on, you're going to want to be able to add more than 1 or 2 parameters, and you're going to want to pass them on the stack, as they say. And that is, you're going to say things like take 0051, push 00 on the stack, push 51 on the stack, then make a function call. Inside the function call, it's going to say, ooh, here's the stack pointer. Let's add 1 to the stack pointer. That'll give us the 51 value. Then add another 1 to the stack pointer. That'll give us the 00 value. And then we can read those back in. But that's a whole level of complexity we haven't got anywhere near. So at this point, we have our 80 instruction. And 80 is just jump regardless, jump short no matter what the flags are set to. And jump back to 4.3, which is our loop. And that is this instruction. Jump short back to 4.3. 4.3 is where we load from the data register, and the loop continues until we hit a 0, at which point we fall through and this instruction is called. So we can single step through that a whole lot by hitting the correct key. Or we can go ahead and let it run until it's done. Let's go up to this level. If we start single stepping, you can see there's a whole number of steps that go by here. We're adding 1 to the data pointer again. And now we can print the L. Takes a few steps. So because of all of that extra time spent, 16 clock cycles necessary to add 1 to the data pointer for each time we print a character, well, that would be why the first hello world is super fast and the second hello world is really slow. Oh, it changed the code again. Make sure we save it. Make sure we have reloaded it. That is still not behaving the way it should. What did change that did not, oh, because I went to 43, probably. Yeah, that needs to be 40 instead of 43. And it's not actually a call yet. It's a jump. Actually, is it a jump? Did I completely read that wrong? It's a long jump, but wouldn't be a big deal. That looks right. Reload. Reload and go. So we actually have a way of counting the clock cycles that are going on here. So if I close that, clear the count, the cycle count up here, zoom in just a hair bit more while we're doing this. We've got that cleared. We reset. So from startup to printing out hello world character by character, it took us 65 cycles. Now 17 of those cycles are just the boot up of any program. So now if we tell it to print hello world without the exclamation mark, but doing that loop where we are spending all our time incrementing the data pointer, that takes 496 cycles. Did I not reset it? Reset. Now we go. Right, 431. So it takes significantly longer to do it in a loop with a function that uses the data pointer to decide what character to print next than it does just writing it in hard code. But obviously hard coding it is not practical in the long term. So let's see. Let's go back over to our code. And what I wanted to do, well, there's your problem. So you can't reuse the addresses, otherwise you just overwrite what was up here. Luckily, there's nothing between. Actually, 21 I think is supposed to be the correct address. All right, so this line 40 got overwritten. So we want to functionalize this, well, or rather we have functionalized the print. Now we want to print something other than hello world. And so for that I have a number of lines that I've set up as sort of like a teleprompter and given them all names, line 1, 2, and 3, and they all have starting locations. So that's all in ROM as well, but we're not calling to print those. So let's see. Print hello world there. And we do a halt. And then it goes to 21. So this is going to be the new 21, where we're going to load into the data register the address of line 1. And scroll right way down here, you see line 1 starts at 0100. And we do that in Little Endian, so it's 0001. Or rather here we do it. And then again, instead of the long jump function, we want to call that function. So calling that function is the 9.6 instruction. And we want to go to 0040, which is not this line, it's this line down here. So for now, we're going to comment those lines out. So what this will do is, after we print hello world and we're stopped, if we go again, it'll set up the location for line 1, call the function to print the function, print line 1, and then inconveniently do nothing else after that. So we want to halt. And that means that at address 00 to what? Well, that's 21, 22, 23, so this is address 24 now. We want to halt, which is 11. Save that. Reload it. And let's go look at it from here. Now we did hello world. We tell it to go. It does hello world inconveniently. Right, 2 1 2 0 2 1 9 6 4 0 0 0. And well, that would be why. Again, we don't want it to be 40 because that's going to reload our data register again. We want to skip down to 4.3, which is why this was 4.3 to begin with. Save. Reload. Reset. There's hello world. And it goes off into the weeds or something. Actually, it seems to have halted on 11. Data pointer is 1. Oh, that looks backwards. And let's see, the instruction pointer is 46. So, instruction pointer got to 46. Here's 46. So we halted. If we came in here, load that. Right. 76. All right, well, we're going to run it up to that first part, and then we're going to start single stepping again. Turn off the clock, clear the halt flag. Sure enough, it's on a 96 instruction. 96 is loaded as the instruction. It says now go look at DRAM based on the stack pointer, which is this location. We're going to put on the stack location our current location. So we're going to store 00 and 21 down here in memory, so we know where we came from. Then we're going to come back, and we should load 43 into the temp register, 00 into the high part of the instruction pointer, 43 in there. Now our instruction is at 43. Our next instruction is the 42 instruction. We load that. Double check our source. Sure enough, we jump to 0043, which is a 42 instruction, which is, I see. Oh, you'll notice our data register is 0, correct? Since our data register is 0, when we read from that location in RAM, we're going to get a 0. Actually, we're going to read that location in ROM, which, if you remember from earlier, is our reset vector. So we read the 08 character into the B register. We then copy that 08 character out to the port, and then 08 in the ASCII table is a whole lot of nothing that's printable. So nothing shows up because the ASCII code for 08, let's go find that real quick. Come on, you. My double clicking seems to be messed up. So we're going to read in 8 in hexadecimal, and that is no character. So we don't see anything. And then, sure enough, the next character that it reads from, going to add 1 to the location here. So now our data register is 1. It goes and reads 1, which is a 0, and because it's a 0, we end up halting. And that's all because our data register wasn't set correctly. Let's see why that is. It should have been right after here, that 96. Oh, well, that would be why. You'll note that we have duplicated our instruction location. So what this wrote out the load, this erased it. So this actually needs to be 0024, and 4 plus 3 is 7, so 0027. Now we have our things properly located. Save it. Reload it. You might have noticed that blink change right there. Reset. Run full speed. Now go. When last we met, I showed how to write hello world. Character for character directly into the ROM. And that would be the first line. So that's our one line printed from the function. Now let's print the rest of them. Now that we got most of the bugs worked out, we just have to make sure we don't duplicate and stomp on our own code. So the next thing we want to load is, let's see, the address is 7001, since we're switching from big to little endian in our head. And we actually don't want to halt right now. Two 4 2 7, and this is the new location for line 2, 7001.
Unfortunately, I have to go. It's very late here. Nice live stream. Love the complexity.
Is that Yao?
Yeah.
Hey, thanks, Yao, for showing up. You're our biggest fan.
We love you, man.
Love you, man. Have a good night. So we're going to load that next line address and call the function again. Should copy both lines to be consistent here. So now we're going to print line 2. All right, come on now. Type 2. And this is actually the same location. The function's always in the same, located at the same spot. So that doesn't have to change. But we again, make sure. Now I would say if we add 3 to 27, we get 30, right? Yeah, in decimal. Instead, we're in hex. So 27 is this location. 28, 29, 2A in hexadecimal. We have 6 letters to go. Oh, that's what's wrong. Caps lock is on. So now we're going to start at 2A, call the print function for line 2. Now we're going to load line 3, which is 5002. right? Because that is actually 0250. Again, big little Indian. And this is line 3. How many lines did I have anyway? 4 lines, so one more. Oh, I should. No, I could do this number where you actually just copy the information instead of relying on your short-term memory. Line 3. This is A02 is line 4. And now that we've blocked and copied, obviously we're not going to write to the same location over and over again. So again, 2A, this is 2A, 2B, 2C, 2D. E, 2E, 2F, 30. 30, 1 and 2, 3, 3. So it gets a little easy while you're still under 10. And it's consistent because they're all 3 byte instructions. So let's double check with 21 to 24, 27.
I'd like to thank you, the winner of the giveaway you did when you passed through that thing.
Oh, cool.
I brought an Arduino kit and I'm learning programs. Hey, that's cool.
Oh, cool. Well, you'll luckily be working at a much higher level than this.
That's super cool.
Yeah, let us know what you build. It'd be like cool to see. And then also, if we get to 512 subscribers, we'll do another giveaway of $100 value. Something. We'll figure out something when we get there. So let's save that off. That should print line 1, line 2, line 3, and line 4. And you'll note we're calling the same function to print. We're just changing the location we start the print function at. And then one additional thing, we don't want to start at 08 anymore and print hello world. We want to start at the point of our program that's useful, which is instruction 21, where we print out all 4 lines. So at our reset vector, we'll make that 21. So that'll just skip over all of this code and start where we're printing the lines. Back over here in the computer, load the image, and back to the desktop view. So not having a good time with the double click. All right, reset. When we last met, I showed how to write hello world, character for character, directly into the ROM. Why'd you stop? What'd you go stopping for? Looks like it hit a halt instruction. Let's see. Sure enough, we've hit a halt instruction at 46. Ah, I see what 47. The problem is. 46 being the instruction pointer, 46. And it's the instruction 11, which we looked at before. And sure enough, that's because we were only calling this function once. Now that we're calling it multiple times, when we're done printing a line and we get to a 0, we want to return from this function call. So to return from a function call, it is return long or 9-7. Again, once you start playing with this long enough, you remember in the 8s, in the 80, 81, 82 are the jump instructions, the jump short. 96 is a call and 97 is a return, or 96 and 97 as I forget over and over again. So now this will actually return, and then we'll actually go ahead and we're going to go ahead and stop at 20 so that I can single step through one call and return. We'll just run through it. Let's just go for broke, right? This is what we call the burn and churn cycle. And some machines is easier than others and takes a minute. Some machines take 5 minutes. I've had horrible targets that take an indeterminate number of minutes to reboot. And so making a one simple test and testing that one change sometimes can make things take forever. So we made that change. Go back up to the main view. Reset. Line 1 prints out again, and I've read it 3 times or something, I know. While it worked and was pretty fast, it had drawbacks. It took up a lot of code space, 2 bytes for each character in the message. It was not easily edited, and there was only one message shown at one time in the code. In this video, I will show how we can implement a function to overcome these drawbacks with only a minimal trade-off in performance.
Let's have a great night. Bye.
Bye. So stick with me as we jump back into the deep end of computing with the UP 5108 virtual microcontroller. Hello world, hello world. Why'd you do that? Actually, I know why I did that. It did that because when we were done with our program of printing all of the lines, we didn't do anything else. We actually just fell through into print hello world using a loop. Because if you don't tell it to stop, it's just going to keep executing instructions from 3.6 all the way down until it finally reaches 5.0. Well, not 5.0, 4.0. 4.0 then actually loads 5.0 and calls a print and so on. So this is where we want to uncomment our halt instruction. And instead of 3.6, we want to be at 3.7. Save it. Reload it. Retest it. And while this prints, I'll go ahead and have a swig of water. Let's see. So actually this was supposed to be like that. Over here. There we go. Don't you see me reading from my teleprompter now?
No.
My 8-bit teleprompter. It's actually not what teleprompters would normally do. Obviously, they would print whole lines and then you'd see the lines going up, but it's just because it can only run so fast. In fact, we have this simulation running at the maximum speed of 2,000 ticks per second, but we're actually only achieving 300 or so hertz. So we're actually going quite a bit slower. And then that's 300 hertz for each single clock cycle, and for each character we need at least 18 clock cycles because 16 of them are adding 1 to the data register for each byte. So that should, we're just looking for it to stop and not do hello world at the end. Oh, actually I just noticed. It's just cycling around in circles. Why are you cycling around in circles, printing over and over again? What is that about? Sure enough. Oh, that's because this print line 4, I overstomped it. I actually told it to jump, not to 4300, but to jump to 11, because I overwrote this byte with this byte. So that's 36, 37, 38. This should be 39. So you're seeing all the gory details of what an assembler will do for you automatically. Luckily, most people will never have to work at this level. Reload the image. Reset. All right. Now we're cooking with gas. Cooking with bits and bytes. Let's see how the stream is going. Oh, we got some chat.
I'm in there.
Varktech again.
Did they come back?
There's a Russian or Cyrillic, I'm not sure, name. Arctic. I don't know. I think
What they get from
I'm not sure if they are. Dear Varktech commenters, do you think you're insulting me? I don't know that you are, or if you are. It might well be a compliment. Oh look, it finished. Yay, it didn't print hello world over again.
Oh, that's good.
So we're good to go there. Let's see, we managed an hour 17. That's pretty decent.
Yeah. 3 people most of the time.
Yeah. Just clean up our code a little. Oh, priority puppy interrupt. Come here, puppy.
You said.
Again with
You
the puppy
indicated.
interrupt. She's a good girl.
You indicated.
All right. Do you have something to say? Do you want to do something other than stomp on my nipples?
No.
No, I like stomping nipples. You're poor pitiful. Go on. All right. Okay. So, well, that's more or less what I was looking to do.
Did you get to a happy place?
The next thing would be to add an instruction to the instruction set, or rather, the instruction's already there, I just haven't actually implemented it. So implementing an instruction in the instruction set is not a small task, really. And by not small, I mean would have a lot of a burn and churn cycle. So maybe we save that for later.
Next time.
Yeah. All right. Well, that was good. We got to part of what I was looking for. Yeah, had some fun. I'm gonna have to go Varktech myself somewhere. I guess.
Apparently.
always in the middle of a stream, there's some robocall for a doctor's appointment. All right, let's see. We got that, and that done. Let's see. Vark Tech. Don't know what that would. The Vark learning styles.
I don't know, but don't give it creating displays.
I suppose it might actually be. This sounds fairly mundane. The model of ways of learning. One of ways of learning styles is visual, and so forth. Yeah. So it's like you're doing.
I don't know why people are doing fake stuff in your stream then if it's a normal thing.
I don't know. So. All right. Well, I think we're good to go. Let's see. We'll bring it back to here. Thanks to everybody who showed up. And we'll be signing off for now. And maybe we'll manage to cut this up into a decent episode. If not, we'll just leave it like this. Bye.